Recording is not on. I have activated it now. Okay. Now, let's see question 10. As I mentioned, this is the exercise. We can look at it together. Basically, it's very similar to the previous one. Stock A, stock B, and stock C are the three stocks. You have to estimate the value at risk of the portfolio using volatilities and correlations of the returns of the individual stocks. So basically, in this case, what you would do, the value at risk of the portfolio, first of all, you have to estimate the value at risk of the individual stocks. So the one of stock A would be equal to the market value of A times the sensitivity would be equal to 1, because the price of the stock is equal, the change in the price of the stock is equal to the change in the price in the value of the position. The volatility of stock A plus alpha, which in this case is says 99%, so it's 2.3. Okay, and you can do the same with stock B, market value of B times sigma B times 2.3, and the value at risk of stock C, market value of C times sigma C times 2.3. Okay. Now, if I want to estimate the value at risk of the entire portfolio, I would have to basically use the square root of the value at risk of stock A squared plus the value at risk of stock B squared plus the value at risk of stock C squared plus all the double products with the correlation. So, for example, twice the value at risk of A times the value at risk of B times the correlation between A and B, which is equal to 0.5. Okay, plus twice the value at risk of A, value at risk of C times the correlation between A and C, which is 0.8, plus twice, and so on, okay? Times the correlation between the two, which is 0, okay? Now, what is more interesting is using the volatility of the rate of return of the portfolio as a whole. Basically, the table is also giving you the volatility of the portfolio, okay? Now, the portfolio as a whole has a market value which is 50, so the sum of the values of all the three stocks. And it gives you also the volatility of the portfolio as a whole, which is 9%, okay? So basically, you can estimate the value at risk of the portfolio simply using the value of the portfolio times the volatility of the portfolio, which is 9%, times alpha, which would be 2.3, okay? This, of course, means that you would be assuming that the distribution of the portfolio returns is normal, okay? And it's an alternative approach, okay? Finally, you can use the approach that we saw in the mapping, which is basically the idea would be to map each individual stock to the stock market index. So, for example, stock A, let's say the value of so the equivalent position on the market index, it would be equal to stock A 15 times its beta, which is 1.4, plus stock B 15 times its beta, which is 1.2, plus the value of stock C, which is 20, times its beta, which is 0.8. This would be the equivalent position in the market index, okay? Therefore, you can then basically compute value at risk using this value on the index, this market value in the times the volatility of the market index, which is 7%, times the scaling factor, which is 2.3, okay? So these are three alternative approaches that you could use to basically estimate the value at risk of this portfolio. Okay. Let's move on to question 11. In a parametric value at risk model, the sensitivity coefficient of a long position treasury bond, expressing the sensitivity of the position's value to changes in the underlying risk factor, is. Now, again, I give you 1 minute and then you give me the answer. Anyone wants to try? No one? Okay, this is quite a strange question. Now, the point is, if I use an asset normal approach, remember, my underlying risk factor is the price change, okay? If I use a delta normal approach, if I use a, let's say, delta normal approach, then the underlying risk factor is the change in the interest rate. Now, therefore, if I use an asset normal approach, my sensitivity is positive, because if the price goes up, I gain. If the price goes down, I lose. Very simple, okay? So the correct answer is A, okay? Another correct answer would have been negative if I use a delta normal approach. And the reason being that in that case, the relevant risk factor would not be the price change, but the interest rate change. And clearly, the sensitivity would be negative, meaning that if the interest rate increase, I would lose in terms of value, okay? So here the correct answer is A. 12, a bank finds that value at risk estimated with the asset normal method is lower than value at risk estimated with the delta normal method. Consider the following possible explanations. 1, because the position analyzed has a sensitivity equal to 1, as for a currency position. 2, because the position analyzed has a linear sensitivity, as for a stock. 3, because the position analyzed has a nonlinear sensitivity, as for a bond, which is being overestimated by its delta. So what is the correct answer? I give you 1 minute and then you tell me. Come on, who wants to try? No one wants to try this question. You still hear me and see me well, right? Okay. Now let's look at them individually. Because the position analyzed has a sensitivity equal to 1, as for a currency position. Well, if the sensitivity is linear and equal to 1, then there would be no difference between asset normal and delta normal, okay? Therefore, this is not correct. Because the position analyzed has a linear sensitivity, as for a stock. As we said, if the sensitivity is linear, again, there would be no difference between asset normal and delta normal. 3, because the position analyzed has a nonlinear sensitivity, as for a bond, which is being overestimated by its delta. This is correct. So the correct answer to this question is C, only 3. Finally, last question. An Italian bank has entered a 3 months forward purchase of 1 million Swiss franc against euro. Using the market data on exchange rate and interest rate reported in the following table, find the positions and the amounts to which this forward purchase can be mapped. Well, basically, you would be, so you're buying Swiss franc forward, 3 months. So you would get Swiss franc in 3 months and pay euros in 3 months, okay? So how can you get these cash flows? Well, you have to, first of all, borrow euro today. So you get cash inflow today in euro, and you have to pay it back in 3 months. You have to buy Swiss franc spot today and pay euro. And finally, you have to invest the Swiss franc. So you have a cash outflow here and a cash inflow here. So this is compensated by this is compensated by that, and you're left with the 2 cash flows that you want. In terms of amounts, how many euros do you have to borrow? First of all, how many Swiss franc you need today? The present value of 1 million, using the interest rate on the Swiss franc, which is 3.75%, 3 months. Okay, that's the amount of Swiss franc you need to borrow. You need to invest today. You have 1 million at the end of 3 months. Okay, which means that the amount of euros you need to borrow today is this times the exchange rate, which is 0.75. That's the amount of euros you need to borrow today in order to buy this amount of Swiss franc that invested would give you 1 million here. So that's the amount of the yen purchased today, and it's also the amount of borrowing in euros, okay? Again, you have the solution in your Excel file, okay? Any questions so far? I'm terribly sorry that I forgot to activate the recording of the session at the very beginning, but I will have a similar lecture for class 16, so I mean anyone can use that. So what I want to do now is move to the simulation approaches, okay, which of course are the next step in value at risk estimation, okay? So very briefly, what are the, we'll look at what are the common features of simulation approaches, and then we'll focus our attention on 4 different methodologies. First of all, historical simulations, which are probably the most common ones, the hybrid approach, Monte Carlo simulations, and finally we'll say a few words about stress testing, okay? Now, first of all, simulation approaches do not necessarily use a normal distribution assumption, okay? They do not assume serial independence, okay? And they take into account the possibility of nonlinear position. We'll see that the nonlinear positions, as I mentioned already, are addressed, this problem is addressed through full valuation, i.e. revaluing the risk positions based on the new simulated risk factors, okay, values. So in this respect, that is the way they address this problem. The way they address the other problems can be different in different approaches. So one way is historical simulation, the other one Monte Carlo simulations, and okay. So first of all, one common feature is simulation approaches are based on full valuation, okay? So every position is repriced for each scenario, and we're not using sensitivity coefficients. That's very important, okay? Therefore, it's important to highlight that from a computational point of view, they are more complex than the parametric approach, okay? It's much more complex to revalue an entire bank portfolio than to use sensitivity coefficients, okay? So that's one important common feature. Second, we'll see that simulation approaches are not using the assumption of a normal distribution of market factor returns. In the case, we'll see it better. In the case of historical simulations, we basically use historical conditions. In the case of Monte Carlo simulation, we can use whatever kind of distribution we want, as we'll see. And they all use the logic of the distribution percentile, i.e. they cut the distribution at the desired confidence level. And we'll see with a simple example what this means. Okay. Let's start with historical simulation, and let's look at how this approach works in terms of estimating value at risk for portfolio. And we start by looking at a very simple example. The explanation is a bit more complex to understand if we don't look at an example. Historical simulations are based on 4 different steps. First, you select an historical sample of market factor returns. Second, you revalue the portfolio for each of the historical values of the market factor. Third, you reconstruct the empirical frequency distribution of the portfolio values. And finally, you cut the distribution at the desired confidence level. Now, what does that mean practically? Let's look at a very simple example. Assume we have a portfolio which is basically replicating the S&P 500, okay? So we basically have US stock market portfolio, okay? And let's look at an historical data series, which is an historical sample, which is made up of 500 daily returns. It's an old sample, but the idea, of course, it's always the same. So what I do is I have, as you can see, in the second column, in the first column is the date, and the second are the different values of the S&P 500 index. In the third column, we have the daily returns from, let's say, the beginning of 2003 to the end of 2004. So we have 2 years of data, which are basically 500 daily returns, okay? Now, these returns in the first part of the table are ordered chronologically, from the first to the last. Assume we are at the end of 2004, okay? Now, in the second part of the table, the same returns are not ordered chronologically, but rather they are ordered from the worst to the best. As you can see, the worst return is a negative 3.6%, which actually took place in a specific date, okay? Based on that return, you have a simulated value of the S&P 500 index, and we assume here that we have a long call. We have we basically bought a call option on the index, okay? Clearly, if we have a long position on a call option, we gain if the underlying index increases, and we lose if the index decreases, okay? So basically, the worst that would have happened in those 500 past days would have been a minus 3.6% return of the market index, which would have been equivalent to a loss in the value of the call option of 2.11. You see that in the last column, okay? At the other extreme of the table, in the bottom part, you can see that the best return would have been a plus 3.5%, and with that kind of return, the value of the option would have increased by 10.4, okay? Now here the point is very simple. If I have a long position on a call option, then assuming I want to know what is my value at risk with 99% confidence level, now my value at risk can be obtained by cutting the distribution at the 1 percentile of the distribution. Therefore, my value at risk with 99% confidence would be 1.65. Why 1.65? Because in that sample of 2 years, daily returns, I would have lost more than 1.65 only 5 times out of 500. I.e., I take the 6th worst return, which is 1.9% negative, and the loss of value of the call option would be 1.65. Now, I would have lost more only 5 days out of 500. And 5 days out of 500 is exactly 1%, okay? So using this approach, I am basically cutting the distribution at this level, which is cutting the distribution at the desired confidence level, okay? If I had a short position on the call option, clearly I would have lost in case of an increase in the market index, i.e. an increase in the value of the call. And here I would have cut the distribution at the other extreme, and the 6th worst here would have been 5.03. Clearly, if I have a short position, i.e. I'm the writer of the option, I'm the issuer of the call option, I lose if the option value does increase, okay? So that's very simply the logic underlying historical simulations. Is that clear to all of you, or is there any doubt of or need of clarification? Everything clear? So now let me ask you, did we make a normal distribution assumption in this case of the market factor returns? Yes or no? Come on, I want at least an answer. Did we make a normal distribution assumption? No, correct. Did we make any other assumption about the functional form of the distribution of returns? Yes or no? Did we make any assumption about the distribution of the returns with this kind of approach? Did we make any assumption? Come on, I'm waiting for an answer. Did we make any assumption about the distribution of the returns? No. Well, remember, we are trying to estimate value at risk. How much could I lose in the future? If I use to estimate value at risk the potential loss in the future, if I use the historical returns, what kind of distribution I am making? There's always, unfortunately, an assumption when we estimate risk. We always need to make an assumption. What kind of assumption are we making here? come on, we use the history to estimate the future. What kind of assumption are we making? Well, ability to forecast, not really. Exactly. We are assuming that the historical distribution of returns is stable over time. It's going to be the same, no change. We don't know what that distribution is. We're not saying it's normal, it's student T, whatever, but we are assuming that it's going to be stable, it's stationary, okay? Which is quite a strong assumption. Is that a better assumption than the normal distribution? I don't know, okay? But we are making an assumption, okay? Is that clear? Also, take a look at this example. Did we use any sensitivity coefficient? No. We revalue the call option for each simulated scenario. We revalue the value of the call, the price of the call option, okay? No sensitivity coefficient, no linear sensitivity assumption. We're just revaluing the price of the option in each simulated scenario, okay? For example, here are the stock market index simulated values. That's the distribution of the changes in the value of the call option. It's clearly not a normal distribution. It's based on historical market factor changes, okay? Let's look at another example. This is a simple stock portfolio, okay? It's just 100 days, okay? And it's a portfolio that it's equally weighted, FTSE 100, the German stock market index, DAX, and the S&P 500. And you have the history of the last 100 daily returns of the portfolio. Here is chronologically ordered. This is order from the worst to the best, okay? Again, you want 99, you take the second worst. This would mean that if you use minus 1.1% times the value of your portfolio, this is value at risk with 99% confidence level. Why? Because you would lose more than that just one time over 100, okay? And same for if you have a short position. In that case, you cut the distribution at the other side, and you would get 1.3%. Okay. If you want 95% value at risk, 95% value at risk with 100 historical returns, you take the sixth worst, which is minus 0.8%. Only 5 times out of 100, you would have lost more. Okay. Now, what about, we could compare, so people who say argue in favor of the historical simulation approach, they say the historical simulation approach is much better because it's taking into account what really happens in market factor returns. And because there are fat tails, by using historical data, you capture the fat tails. And therefore, historical simulations are more conservative, are better than the parametric approach, okay? Because they capture these fat tails and they tend to be more prudent, okay? So what about if we use this sample and we apply both methodologies, i.e. historical simulations and the parametric approach? So historical simulations, we saw that if I have a long position, value at risk with 99 would be 1.1%. Value at risk with 95% confidence level would be 0.8%. What about the parametric approach? The parametric approach, you just take this historical series of returns, you compute the standard deviation, and then you multiply it by 2.3 or 1.65. Those are the results you get. So for example, if you have a long position and you want value at risk with 95%, historical simulation would be 0.85. The parametric approach would be 1.03. 99%, remember it was 1.12. The parametric would be 1.46. If you have a short positions, again, you have these values. As you can see, in the case of long positions, it is not true that historical simulations are more conservative, more prudent. In reality, the parametric approach with the same portfolio gives rise to higher value at risk estimates. So clearly that depends on the historical sample you're using. If it's an historical sample with significant shocks, it could well be that historical simulations are more conservative. But that's not necessarily the case. It very much depends on what is the historical sample, okay? This is the distribution, the historical distribution compared to the normal one, okay? Okay. Let's try to recap a bit about historical simulation. What kind of advantages do we have? Now, first of all, they are easy to understand and communicate. Now, I can tell you, if I try to explain how historical simulations work in a bank board of directors, it is relatively easy. I simply say, if I take my portfolio and I apply the conditions that actually took place in the last, say, 2, 3, 4 years, then worst 1%, so 99% confidence level, value at risk would be equal to X, Y, Z, okay? This everyone would understand, okay? Now, if I take the parametric approach and I try to explain it, and I say, well, assuming a normal distribution assumption and linear sensitivity, by multiplying the standard deviation, historical standard deviation by 2.3, because of the normal distribution to the value of my position, what I get is, and I lost everyone, okay? So historical simulations are much easier to understand and communicate, okay? Second, there is no explicit underlying assumption concerning the functional form of the return distribution. Third, that's very important, I have no need to estimate the variance covariance matrix because that is incorporated in historical returns. Also, the correlations are captured by the co-movement in the past. So I don't need to estimate correlations, okay? And finally, because of full valuation, it allows me to capture the profile of nonlinear portfolios and also non-monotonic portfolios, which is very important here. Now, to give you an idea of the problem of non-monotonic portfolios, let me give you a very simple example. I assume I have a portfolio which has this kind of sensitivity. Say it is a option portfolio, that's the payoff, and that's the underlying asset price. Say that this portfolio sensitivity is of this kind. That is the underlying asset price, spot price today, and the value of the portfolio, the profit is here. If the price increases, I lose, but then if it increases further, I gain, okay? Now, if I use the parametric approach, and say, for example, I use twice the standard deviation, which is equal to this, I would say, well, if I move from here to here in terms of the spot price, S1, my loss would be equal to this, okay? Now, with the parametric approach, I could say, well, I want to be more conservative and use a higher confidence level, and therefore, for example, increase the price change to S2. Under the parametric approach, my potential loss, my value at risk would be double that. But in reality, moving from S0 to S2 the loss would be 0. Okay? This is because this portfolio not only has a non-linear sensitivity to the underlying market price, S, but it's non-monotonic. It decreases and then increases. Okay. For example, this is a portfolio of options where I have bought both a call and a put option on the same underlying asset. Okay. So clearly, the parametric approach for non-linear, non-monotonic portfolios is clearly biased. Okay. So simulating with full valuation is much better. Okay. What are the disadvantages of historical simulation? Now, first of all, I am assuming the stability of the market factor returns distribution. That's something we said. I am basically assuming that the historical one is a good proxy of the future one. Okay, but there is no guarantee that this is the case. Okay. Second, because of the complexity of revaluing many times an entire real portfolio, this is computationally much harder, takes much more time. Finally, one of the problems we have with historical simulations is the trade-off in the choice of the historical time horizon. A bit like we had with historical volatility in the parametric approach. Here the problem is the following. Assume, for example, that I use an historical sample of 100 days. Now, if I do so, and I want 99% confidence level value at risk, you can understand that I am not properly defining the tails. Because basically, I would have only one data point in the tail. 100 historical returns, and when I cut the distribution at the 99% level, I would have only one historical return in the tail. So I'm not defining the tails well, okay? So the only solution would be to take a long historical sample, say, for example, 3, 4, 5 years. This way I can define well the tails. But if I do so, if I go back, for example, 5 years, what is the problem? The problem then is that the assumption of stability of the distribution becomes very strong and very unrealistic. Because if I go back 5 years, clearly it's not updated, okay? So there is this trade-off between using a long enough historical sample so that we can define the tails well, or but if we use a long historical sample, then the stability assumption is violated. Okay. Now, based on this trade-off, we have the second approach, which is called the hybrid approach, which was originally introduced by Buduk, Richardson, and Whitelaw back some 20 years ago, which is very, very much used in the market out there. Okay, and basically what it tries to do is to combine the best of two worlds, i.e., basically it is using the exponentially weighted approach that we looked at in the parametric approach, i.e., give more weight to the recent data, and at the same time use the historical simulation by looking at historical returns. Let me give you a very simple example of what the hybrid approach looks like. Okay, what you have here is a very simple example of a portfolio with 100 daily past returns, which is the example we saw before. Okay, now as you can see in the first part of the table, you have the dates, you have the simulated portfolio returns, and then you have the weights in the third column, which is basically exactly the same as the one we saw when we discussed exponentially weighted. Now, as you can see, the very last one has a very high weight compared to the first. So the most recent one has a very high weight, 6%, compared to the one very far in the past, which has a weight of only 0.01%. Okay. Now, these are chronologically ordered. Okay. Now, in the second part of the table, what you see are the same daily returns, but this time ordered as we did with historical simulations, from the worst to the best. Okay. Now, what is different here is that for each historical daily return, we have its own weight, which is the one that it gets here in the first part of the table. Okay. Now, what is the difference now with the hybrid approach? The hybrid approach is basically telling you that you have to cut the distribution not by giving the same weight to everyone, which would be 100 return 1% each, and therefore you would cut it at the second one, okay, i.e. 1.12%. But rather, what you would do is look at when the cumulated return, the cumulated weights get to the percentile that you want, i.e. 1%. Okay. So for example, the much worse one, 199, has 0.03% weight. The second one is 0.01%. So the sum of the two is 0.04. Now that is not enough because we want 1%. If we add the next one, each weight is 0.83. So if we add up these three, we get to 0.87. That's very close to 1%, but not yet there. If we get to the next one, which is 1.04, the weight is very high because it is a very recent one, okay? And therefore we get to 3.56 cumulated weight, which is much more than what we want, okay? So in this case, what can we do? We can either be conservative, prudent, and therefore get a here 1.04, so that the sum of the weights of the worst returns is a bit lower than 1%, or get the following one, but it's higher than that, okay? So as I said, we can be either prudent and get 1.09 as the, say, the relevant one, or what we could do is get a linear interpolation, i.e. we know we want something that is between 1.04 and 1.09, okay? Now this something should be much closer to 1.09 than 1.04, because this 0.87 is much closer to 1 than it is this one. We want this level, this value, to be 1%. So we basically compute a linear interpolation like it is computed here, and we get 1.07, which is closer, as I said, to 1.09 than to 1.04, okay? So that's the way the hybrid approach works. It's basically an historical simulation where we give more weight to the recent data than to the very past ones, okay? This is an approach which is quite commonly used in the market because, remember, if I use the hybrid approach and I give more weight to the recent data, I get a more reactive estimate of value at risk than I get with simple historical simulation. And clearly, I get a more reactive estimate of value at risk. Other things equal, the lower is lambda, i.e. the lower is the decay factor that I use to estimate the, different weights, okay? Any questions so far? Is everything clear about the hybrid approach? No doubt, no problem? Okay. Let's move to the third approach, which is based on a simulation approach, which is Monte Carlo simulations. Again, a very short introduction, and then we'll see how an example works here, okay? Now, first of all, where do Monte Carlo simulations come from? Monte Carlo simulations were originally introduced in physics, in the Manhattan Project for the atomic bomb, the so-called Project Manhattan, where a key role was played by an Italian, Enrico Fermi. By the way, I mean, it's nothing to do with our course, but there is such a wonderful biography of Enrico Fermi, which I strongly suggest you to read. Now, the reason there was to try to understand what would have been the consequences of a nuclear reaction, and because that could not be computed with, let's say, a closed formula, what they did, they said, let's try to simulate many times what could be the possible scenarios. And then we take, let's say, the different simulated values into account. Now, these techniques were originally introduced in finance for pricing purposes, not for risk management. And the idea was to, when we have complex options for which we don't have a pricing model which is a closed formula, once again, what we could do is simulate the possible path of the underlying asset price many times, and then look at the different values of the option in these scenarios, and then compute an expected value. So in pricing, the idea was to then, based on the different simulated values, compute the mean, the expected value of the payoff. Now, in the case of risk management, of course, we're not interested in the expected value, but rather we would be interested in the tails, okay? And in risk management, we would basically follow 5 steps. First, we identify the distribution that best proxy the actual market factor returns distribution. That is a very important point. Differently from historical simulations, in the case of Monte Carlo simulations, we do need to make an assumption about the underlying asset price distribution. The underlying market factor returns distribution. Therefore, we need to make an explicit assumption, okay, about the functional form. It doesn't need to be a normal distribution, but we need an assumption. Then we simulate, based on this assumption, the evolution of the market factor many times. We compute, as we did with historical simulation, the market value of our position in each scenario, in each of these simulated scenarios. And then the following steps are the same as in historical simulation, i.e. we build the empirical probability distribution of the changes in the market value, and then we cut this distribution at the desired confidence level, okay? So the final 3 steps are exactly the same as in historical distribution. But the first 2 are very different because we don't use the historical returns. How do we proceed here? We basically typically extract the value from a uniform distribution with a random generator. We calculate the value x of the function corresponding to the extracted value. we determine the inverse of the cumulative function of the original sample distribution, and we repeat this process many times. Now, in order to show you how that actually works, let me actually show you a very simple example, okay? Are you still listening and seeing me well? Okay. Now, I want to show you a very simple example. And usually, I was used to do this example in class using two market factors. Let's call them this way. And the two variables are the height and the weight of a population of students. What I was used to do is ask each one of you to give me a small piece of paper with your height and your weight, okay? They're clearly anonymous. Now, in this case, because we are in remote, we can't do that directly. So what I'm going to use is the data from the class of last year, okay? So what you see here in this file, Excel file, that I will upload in Blackboard, is our 50 data points for height and weight of 50 students, okay? Now, based on these 50 data points, what I did here is compute the average height, which is 174 centimeters, and the average weight, which is 69 kilos. The standard deviation of these two variables, the asymmetry, the kurtosis, and the correlation. As you would expect, the correlation between height and weight is very high, and it's positive, equal to 0.8, okay? Now, how do we go about with this example? First, let me show you how we do with Monte Carlo simulations. Okay, I have to connect it once again. So the point is the following. We typically start from a uniform distribution, say from 0 to 1, with a random generator that you can also find in Excel, okay? And here we have the cumulative of, say, for the time being, we assume a normal distribution, okay? So all these values from 0 to 1 are equally likely, okay? They have the same probability. And here we have our, let's say, standardized normal distribution, okay? Now, say we extract one value from here, which is equal to 0.2, and then we find the corresponding value on the normal distribution, standardized, Z, okay? This was 0.2, sorry. Now, an alternative value would be 0.4, is having another corresponding value on the, this is Z1, this is Z2, okay? As you can see, these values from 0 to 0.2 and this value from 0.2 to 0.4 have the same probability, but here in the normal distribution, they get a much different interval. This is much longer, but with smaller area. So this area is the same as that one, okay? And these are standardized normal, okay? So as you know, Z is equal to the mu minus, is equal to X, our variable, minus mu divided by sigma. So if I want to get my true variable X, I need to use Z times sigma plus mu, okay? Now I can simulate many values of this let's say, uniform distribution from 0 to 1 using a random generator. And following this reasoning, let's go back to our example. Again, I will upload this file on the Blackboard, and you can see how it works. So in the second sheet, what you have is a random generator from 0 to 1. And these are 1,000 values of this random 0 to 1. If I press F9, these are different 1,000 values, okay? Now, here I have the corresponding standardized normal value, exactly what we did. Oh my God, okay. Sorry. Exactly like we did here. From the random generator, from the random values from 0 to 1, we get the values of the corresponding normal distribution, standardized. Then, from here, we move to the normal distribution. How do we do that? We take the value of the standardized normal, we multiply it by the standard deviation of our variable, and then we add the mean. We basically take this data, we multiply for height for the standard deviation, and then we mean. And what we get here is one simulated value for height. As you can see, the simulated value is 189, okay? The following one is 161, then 182, 164. These are 1,000 simulated values of height, okay? Now, the same can be done for weight. We can simulate 1,000 values from 0 to 1, the corresponding standardized normal, and the corresponding value of our variable weight, okay? Now, unfortunately, these two values have been simulated independently, one from the other, i.e., assuming that there is no correlation, zero correlation. In reality, the two are strongly correlated, okay? So how can we introduce correlation? This can be done by using a methodology which is called the Cholesky Decomposition. That's basically a methodology that is starting from the variance-covariance matrix. The one you see here that I'm currently highlighting is the variance-covariance matrix, which is decomposed into two matrices, the ones that you have here. One, as you can see, is the transpose of the other, such that the product of these two matrices is exactly equal to the variance-covariance matrix. If you multiply these two matrices, you get exactly the variance-covariance matrix. Now, using this transpose of these two variables, you can obtain a simulated value of the second variable, which is weight, that actually takes into account correlation. As you can see, this is also taking into account the Cholesky decomposition. To give you an idea, let me just reason on value at risk. Now, the example I'm making here, and you have to follow with attention here to understand, is let's assume that you have a portfolio with two positions. One position is you're long on a future on height. So you bought a future on height. Therefore, if height is very high, you gain. If height is very low, you lose. More specifically, here we're assuming that you bought a future with a future price of 175. so 175 centimeters. If the simulated value is higher than 175, you gain. If the simulated value is lower than 175, you lose. At the same time, you sold a future on weight. And the future price here is 75 kilos. So if the simulated value on weight is higher than 75, because you short the future, you sold the future, you lose. If the simulated value of weight is lower than 75 kilos, you gain. So you're basically long on height, short on weight. Okay? Now, basically, what you could do is then estimated value at risk, 95% confidence level or 99. How is this computing value at risk? Well, if you can see in the formula up here, it's basically cutting the distribution at the percentile level. Now, the first two values, 95 and 99, are not reflecting correlation. And clearly, the values of value at risk are much higher because you have a natural hedge. You are long in one variable and short in the other, and the two variables are positively correlated. Therefore, there is a natural hedge. If you don't take into account this hedge, this correlation, the value at risk is much higher than if you take into account correlation. This correlation is based on the portfolio value that you have here, which is also reflecting correlation, while this is not, okay? And you can see that in the charts here. This is non-correlated values of height and weight. Now, as you can see, this is basically these dots. Each dot is a combination of weight and height. And here the two are completely uncorrelated, okay? Now here on the other side, they're clearly correlated. And this is computed taking into account the correlation, the positive correlation between the two variables. Now, because you're long in one variable and short in the other, then this positive correlation for you is a natural hedge. And you can see that in these value at risk estimates, okay? Now, I hope that very simple example gave you at least an idea of how Monte Carlo simulations work. But of course, as I said, I'll upload this file and you will be able to see how it works. So this is what we just discussed. Now, the example you have in the slides is very similar. The example here is that of a bank that has bought a call option on the stock market index Italian one with a maturity of 1 year and a market value of 9.4. And it makes some assumptions about the risk-free rate and the volatility of the market factor return. And it's assuming normal distribution with a standard deviation of 1.5. Now, what it does, it simulates many times a random value from 0 to 1. It computes the inverse of the standardized normal. It computes the actual normal, exactly as we did in our Excel example on height and weight, the value of the call option, okay, and the change in the value of the call option. And then, based on those changes, you can rank them and then basically compute value at risk, okay? And you can do that with the number of simulations you want, 1,000, 2,000, 10,000, okay? Which of course allows you to define very well the tail, not encountering those problems that you have with historical simulation. Now, if you have a portfolio, as we mentioned, you need to inject correlation because Monte Carlo simulations do not capture correlations automatically. And that is done with the Cholesky decomposition, as we mentioned, and it's shown in the Excel file that we discussed before. And this here is actually shown with an example with two positions, a call option long on the Italian stock market and a call option short the sale of a call option on the German market. Okay, again, assumptions about returns and volatilities, and the assumption is that of a positive correlation of 0.75. Like we did with height and weight, you simulate many times, here is 1,000 times, the values of the underlying asset, okay, using the assumptions about the distribution. And then here is without correlation, and here is with the correlation. And that's what you get then for value at risk, 99 and 95% confidence there, okay? Just as we did with height and weight, okay? Now, to recap, what are the advantages of Monte Carlo simulations? First of all, like in the case of historical simulations, the evaluation, therefore, we don't apply sensitivity coefficients, and this is very useful and more precise, but of course it's more complex. Flexibility, remember, we need to make an assumption about the functional form of the distribution, but we can use whatever we want, okay? Usually there are softwares that tell you what known distribution best fits the historical one. And also, Monte Carlo simulations allow you to estimate value at risk of portfolios which are path dependent, meaning that their final value not only depend on where the market factor is at the end of the period, but also what is the path that it has followed over time. And this, of course, is a very important advantage. What are the problems of Monte Carlo simulations? First of all, differently from historical simulations, you need to estimate correlations, and therefore there is a stability problem. Second, they are very computationally intensive. And third, you need to make an assumption, an explicit assumption, about the functional form of the distribution of market factor returns, okay? This is very important. Now, Monte Carlo simulations are more and more common because, of course, the problem of being computationally intensive has become less and less relevant over time, given the fact that we now have more computing power, and therefore there is, this problem is much less relevant. Okay. Okay. I would stop here, but ask you if there are any questions or doubt. Of course, next time we'll start again from here, summing up all what we did today. Okay, and we'll also see a few questions and exercises. Okay, any question? Okay, so I'll speak to you next Friday.